High above the Earth's surface lies a layer of the atmosphere called the stratosphere. This layer extends from about 10 kilometers to 50 kilometers above the ground, sitting just above the troposphere, where most of our weather occurs. The stratosphere is characterized by a gradual increase in temperature with altitude, a stark contrast to the troposphere below. It is known for its stability and lack of weather as we know it. Unlike the troposphere, the stratosphere is relatively calm and free from the turbulent weather patterns that we experience on the surface. This stability is due to the presence of the ozone layer, which absorbs and scatters ultraviolet solar radiation, creating a temperature inversion that prevents vertical mixing. Within this layer during the winter months, a large-scale weather pattern forms called the polar vortex. The polar vortex is a persistent large-scale cyclone located near the poles, and it is strongest during the winter when the temperature difference between the polar regions and the mid-latitudes is greatest. This swirling mass of cold air is held in place by strong winds, effectively trapping the frigid Arctic air. These winds, known as the polar jet stream, encircle the polar vortex and act as a barrier, preventing the cold air from spilling southward. The strength and position of the polar vortex can vary, influencing weather patterns far beyond the polar regions. The polar vortex plays a crucial role in regulating global weather patterns. Its influence extends to the mid-latitudes, where it can affect the frequency and intensity of weather events such as cold snaps, heat waves, and storms. When the polar vortex is strong and stable, it tends to keep the cold air confined to the polar regions, resulting in milder weather for the mid-latitudes. Its strength and position influence the jet stream, a fast-flowing air current that guides weather systems across the northern hemisphere. The jet stream acts as a boundary between the cold polar air and the warmer air from the tropics. When the polar vortex is strong, the jet stream flows in a relatively straight path, leading to more predictable weather patterns. A strong polar vortex typically keeps the jet stream flowing smoothly, leading to more predictable and often milder weather across mid-latitudes. However, when the polar vortex weakens or becomes unstable, the jet stream can become wavy, allowing cold Arctic air to plunge southward and warm air to move northward, resulting in more extreme and unpredictable weather. However, the stability of the polar vortex can be disrupted by a phenomenon known as Sudden Stratospheric Warming, or SSW. SSW events occur when there is a rapid increase in temperature in the stratosphere, often by as much as 50 degrees Celsius over a few days. This warming weakens the polar vortex, causing it to split or become displaced. These events can have significant impacts on weather patterns across the globe, particularly in the northern hemisphere, leading to periods of extreme cold and winter storms. When the polar vortex is disrupted, the cold Arctic air can spill southward, bringing frigid temperatures and severe winter weather to regions that are not typically accustomed to such conditions. Understanding SSW and its effects on the polar vortex is crucial for anticipating and preparing for potential weather disruptions. Meteorologists and climate scientists closely monitor the stratosphere and the behavior of the polar vortex to improve weather forecasts and provide early warnings of extreme weather events. By studying these patterns, scientists hope to better understand the complex interactions between the stratosphere and the troposphere, ultimately leading to more accurate and reliable weather predictions. Sudden stratospheric warming, as its name suggests, is characterized by a rapid increase in temperature in the stratosphere. This phenomenon is not just a minor fluctuation, but a significant and abrupt change that can have far-reaching effects on weather patterns and atmospheric dynamics. This warming, which can be dramatic, reaching tens of degrees Celsius within a matter of days, disrupts the normal temperature gradient of the stratosphere. The stratosphere, which is the second major layer of Earth's atmosphere, typically has a stable temperature gradient, with temperatures increasing with altitude. However, during an SSW event, this gradient is significantly altered. The temperature gradient is crucial as it influences the strength of the winds that maintain the polar vortex. The polar vortex is a large area of low pressure and cold air surrounding the Earth's poles, and it plays a key role in regulating the climate and weather patterns of the northern hemisphere. SSW events are triggered by the upward propagation of large-scale waves of energy, known as Rossby waves, from the lower atmosphere into the stratosphere. These waves are essentially large-scale meanders in high-altitude winds that are influenced by the Earth's rotation and the distribution of land and sea. These waves, originating from disturbances in the troposphere, the lowest layer of the atmosphere where our weather occurs, can break in the stratosphere, much like ocean waves crashing on a shoreline. The troposphere is a dynamic layer where weather systems, such as cyclones and anticyclones, generate these Rossby waves. This breaking of Rossby waves disrupts the normal west-to-east flow of stratospheric winds, ultimately weakening the polar vortex. The polar vortex's strength and stability are dependent on the consistent flow of these winds, and any disruption can lead to significant changes in weather patterns. The extent of the weakening depends on the intensity and persistence of the wave activity. If the wave activity is strong and sustained, it can lead to a more pronounced weakening of the polar vortex, which can have a cascading effect on the weather in the lower atmosphere. In some cases, the warming can be so intense that it leads to a complete breakdown of the polar vortex, splitting it into two or more smaller vortices, or even reversing the direction of its winds. This breakdown can result in extreme weather events, such as severe cold spells in Europe and North America, as the disrupted polar vortex allows cold Arctic air to spill southward. Historical records show that SSW events have been linked to some of the most severe winter weather events in recent history. For instance, the infamous cold wave of 2013 to 2014 in North America, which brought record-breaking low temperatures and heavy snowfall, was associated with a significant SSW event. Scientists use advanced climate models and atmospheric data to predict SSW events. These models take into account various factors including sea surface temperatures, atmospheric pressure patterns, and the behavior of the jet stream. Accurate predictions of SSW events are crucial for preparing for potential impacts on weather and climate. Understanding and predicting SSW events can help communities and governments implement mitigation strategies to reduce the impact of extreme weather. This includes preparing infrastructure for severe cold, ensuring adequate heating supplies, and developing emergency response plans. Sudden stratospheric warming is a powerful reminder of the interconnectedness of Earth's atmospheric layers and the complex dynamics that govern our planet's climate. By studying these events, scientists can gain valuable insights into the mechanisms driving climate change and improve our ability to predict and respond to extreme weather events. Ongoing research and advancements in technology continue to enhance our understanding of SSW events. Weather balloons, satellites, and other observational tools provide critical data that help scientists monitor the stratosphere and improve the accuracy of weather forecasts. Public awareness and education about sudden stratospheric warming and its impacts are also essential. By increasing knowledge and understanding of these phenomena, we can better prepare for and adapt to the challenges posed by extreme weather events. While sudden stratospheric warming events can cause significant disruptions, the stratosphere eventually returns to its normal state and the polar vortex re-establishes itself. This natural resilience of the atmosphere highlights the dynamic and ever-changing nature of our planet's climate system. The weakening or collapse of the polar vortex due to sudden stratospheric warming, or SSW, has a profound impact on weather patterns in the northern hemisphere. This phenomenon can disrupt the usual flow of the atmosphere, leading to significant changes in weather that can be felt far from the Arctic. Normally, a strong polar vortex effectively confines the frigid Arctic air to the polar regions. This containment helps maintain a stable and predictable weather pattern, keeping the cold air locked in the Arctic and preventing it from spilling into lower latitudes. However, when the vortex weakens, the jet stream, which meanders below it, becomes wavier and more susceptible to large north-south excursions. This waviness can cause the jet stream to dip far south in some areas and rise far north in others, leading to unusual weather patterns. Think of the jet stream as a river and the polar vortex as its banks. When the banks are strong, the river flows smoothly and predictably, much like a strong polar vortex keeps the jet stream in check. A strong vortex keeps the river flowing smoothly, ensuring that the jet stream follows a relatively straight path, which helps maintain stable weather patterns. But weaken the banks, and the river becomes erratic, spilling its contents over the sides. Similarly, a weakened polar vortex allows the jet stream to become erratic, leading to unpredictable and extreme weather events. A weakened polar vortex allows the jet stream to buckle, driving cold Arctic air southward and drawing warmer air northward. This can result in dramatic shifts in temperature and weather patterns, affecting regions far from the Arctic. This exchange of air masses leads to dramatic temperature swings and an increased likelihood of extreme weather events. These events can range from severe cold snaps and heavy snowfall to unseasonably warm temperatures and unusual weather patterns. Regions accustomed to mild winters may experience intense cold snaps and heavy snowfall, disrupting daily life and causing significant challenges for infrastructure and transportation. Meanwhile, areas that are normally colder might see unusually warm temperatures, leading to a range of impacts from early snowmelt to changes in local ecosystems and wildlife behavior. The impacts of a polar vortex collapse can be felt across the entire northern hemisphere, affecting millions of people. From agriculture to energy consumption, the ripple effects of these weather changes can be profound, influencing various aspects of daily life and economic activities. Understanding the dynamics of the polar vortex and its potential to disrupt weather patterns is crucial for preparing and adapting to these changes.